Hey, how are you going? Do you remember in my last video I have discussed power series. We have defined the power series like this. So this is called a power series in X, or this is a power series around 0, right? So in this video we are going to talk about Taylor series and McLaurin series. Think you have already learned Taylor and McLaurin in first semester, I think, right? So, any power. So this power series, I suppose. Let's take this power series here. So we can represent this power series as a function. So here x is a variable. So because of that, we can represent this power series as a function. So for instance, so this is a variable. If that variable is equal to r, so r is the common ratio, so that power series becomes r to the n, something like 1 plus r to the power 1 plus r square, and so on, dot dot, right? So this is a geometric series, so this one is convergent. This one converges to 1 over 1 minus r whenever mod of r less than 1. So we know that this one converges to this value here. So we can represent this one here, this power series, as a function. So this power series is equal to 1 over 1 minus x whenever mod of x less than 1, right? The question is, now we are given a function. Right? Then we are going to find a power series, such that this fx is equal to a power series. See, power series in x minus a. This one is true. This power series converges to fx on this interval. So here r is the radius of convergence of this power series, and for each x, this power series converges to this function. So now we are going to find a power series such that power series is equal to f of x. That power series converges to that function over the intervals, over this interval here, right? Actually, this can be done for infinitely differentiable functions. Oh, so you can say, if if uh, if if f belongs to C infinity, that means infinitely continuous functions, that means infinitely differentiable. F is continuous. If f is infinitely differentiable, some interval around a, then we can represent that function as a power series, right? So Taylor found a particular power series when the function is infinitely many differentiable in a given interval around that point, right? So around a here, so around a, if the function is infinitely differentiable around a, so around a means, yeah, I mean, so the x is delta something like this, a minus delta, a plus delta. So if f is continuous, so delta is a positive value, right? Continuous on this interval. Now infinitely differentiable on this interval, then you can represent this function as a power series. Taylor did that, so we call that expression Taylor series. Let's see how do we find the Taylor series for the function, infinitely differentiable function, right? Here, look at this. Sometimes a power series has uh, power series. A function has a power series expansion at a point A. Sometimes it doesn't, right? One of the benefits of existence of such an expression is that we can approximate value of function with polynomial. So definitely you can approximate. If you have complicated or very complicated function, you can approximate that function as a as a polynomial. We know that polynomial is smooth, very differentiable, continuous, right? Very smooth function. So that's one of benefits. Another is that we can actually find the sum of some series. Yeah. So if a function has a power series expansion at that point, can we tell what the power series expansion is? There are different power series, but Taylor found a particular expansion. We call it Taylor expansion, right? To find Taylor expansion, f need to be infinitely f needs to be infinitely differentiable uh, on an interval including this point, right? So let's discuss that, right? So for which value of x do the value of f and the sum of the powers coincide? So definitely you can see that. All right, let's find that out. Suppose f is infinitely differentiable, right? And assume that f of x has a power series. So let me assume that f, the function f has a power series in x minus a, or f has a power series around a, point a, right? So so if this function infinitely differentiable, right? So we can differentiate this expression, this equation, right? So first of all, so we don't know these coefficient. So we are going to find these coefficient CIs, right? So how do you find the first coefficient? It is very easy. Here you have x minus a terms. So you can kill these terms by subbing a into the equation. So when you sub a a into the equation, you can calculate c naught coefficient. So how do you compute the next coefficient? So how do we find the next coefficient? This is where differentiation comes into play. So you can differentiate this equation, right? Then what do you get? So this becomes 0 f prime. The left hand side is f prime of x. The right hand side, this makes equal to 0 when you differentiate once, and c1, and when you differentiate this term here, you get 2 in front of c2, 2 times c2 x minus a to the 1, and other all terms have this difference, x minus a, right? So now you can kill these terms by subbing a into here. So then f prime of a is equal to c1. Now so you do this process continuously, right? And you can find the pattern, you can catch the pattern, f double dash double prime of a, you will get c2 divided by factorial 2, and if you find the nth c sub n, you will get nth derivative of f of a divided by factorial n. Alright, so therefore finally we found the coefficient of that power series, which is equal to and goes from 0 to infinity f and nth derivative of f at a, evaluated at a, divided by factorial a, and that difference a, x minus a to the power n. So this is called the Taylor expansion. So Taylor expansion around a, right? So here we go. So this is the Taylor expansion about a or around a, anything, you can say anything. So if you have a function which is infinitely differentiable, then you can find this Taylor expansion at a given point. So that function should be differentiable, infinitely differentiable at that point. Then you can find a Taylor expansion, the Taylor expansion of that function. Let's discuss some couple of examples. So the function is given. We know that this function is infinitely differentiable at any point. This one is very smooth and infinitely differentiable. Then you can find the Taylor expansion at any point on real line, right? So what are derivatives? This is the first derivative here. So you get the same function, right? Now you have to plug. So the Taylor expansion of that. So you have to evaluate those derivatives at that point here. So f prime of 1 is equal to this, like that. And you can sub those values into the Taylor expansion, you get the Taylor series of that at a equal to 1. So this is the Taylor expansion of e to the x around a equal to 1. So if you find the Taylor expansion of a function around 0, they give a special name, McLaurin. McLaurin found that expansion, so we call it McLaurin expansion. So we know that the McLaurin series is the special case. It's a special case of Taylor expansion. The McLaurin series is same with the Taylor expansion around 0, right? So let's find the Maclaurin series for this function. This one is infinitely many differentiable at 0. Then you can find the Maclaurin or say Taylor, right? So you can find the Maclaurin series, and finally you get, so this is the Maclaurin expansion. This is called Maclaurin. So this is a special type of Taylor expansion because so here we consider the Taylor expansion around 0. They give a special name called Maclaurin series, right? So you can find, so this is the series, Maclaurin series for this function. So if you look at the radius of convergence of this expansion, you see that the radius is infinity. Just apply ratio test to find the radius of this power series, right? I think you know that. So in this note, there are a lot of examples discussed. You can go through that if you have time, right? So let's recap what we did. So if you are given a function, right? So we can find a power series for that function if the function is infinitely differentiable at a given point, say a point at A, right? Then you can find an expansion, power series expansion like this around that center A, right? So Taylor did that one. So Taylor did that one. So if the function is infinitely many differentiable at that point, then you can find the expansion, Taylor series expansion. So, and you can find the radius of convergence or interval of convergence, in which this infinite power series converges to, and so on, right?